4.7 deals with inverse trigonometric functions, and what we're going to do is now take a look backwards at what we've been doing all along. So far with trig functions, we have figured out that there are certain side-to-side ratios that are linked for any kind of angle on a triangle. So we would say, let's input an angle into our trig function, and we're going to get a certain relationship to a side-to-side ratio based on that angle. Now we're going to look at the backwards route and say, well, if for every angle there's a certain side-to-side ratio, well then of course, if you look at the side-to-side ratio, you can link it back to an angle. So now we're going to be looking at the side-to-side ratios as our input, and we're going to then be figuring out what angle goes with the side-to-side ratios. Okay, so again, instead of looking at an angle in a triangle and figuring out what's the side-to-side ratio, we're going to be looking at the side-to-side ratio and figuring out the angle. So that's the main understanding of what inverse trig functions is going to require. So you're going to want to walk away with that. Then with this understanding, we'll be able to evaluate inverse trig functions. And we're also going to have to look at certain domains and ranges that will restrict our answers. So an inverse trig function, as I've kind of tried to explain, which it's a little confusing, but I mean it's the backwards motion, or it's the opposite operation to what we've been doing with trig functions. Here's a quick analogy. Just like all of our other operations that we've been dealing with, we needed ways of undoing them. So division has multiplication, right? You have multiplication to undo your division. They're inverses. So likewise, we need something to undo this sine function. What if we want to work backwards, right? That's from these inverse functions. This is a certain notation. I'll introduce you that in a little bit. But we need something to undo our trig functions to work backwards. Alright, so a quick reminder of what inverse functions were. Keep in mind that the x and y rows swap. Process that we used was we would go ahead and switch the x and y roles and then solve for your y. So don't forget, this is just a notation that it is an equation with for every input there is only one output. That's what this is saying. For every input there is only one output in this equation. But overall it's just an equation, so I'm going to label it like this for now. Okay, and then we would go ahead and switch those roles and we would solve for our y. And so I think it is of no surprise to us at this point that, yeah, this makes sense that multiplication of 4 onto a number, the backwards look at it would be saying, well, then take that number and divide it by 4. If you were to look at the xy table of this y equals 4x and then y equals x over 4, what we would get is that swap. So plug in 1, you're going to get 4. Plug in 2, you're going to get 8. So the idea is, well, look at it with this relationship. Take one of those values, that 4, and say, okay, you're going to get 1. 4 divided by 4, you get 1. You plug in 8, you're going to be back to that original input, you're going to get 2. So just like, I mean, if you had something like this, 4x equals 8, you know that you can use division to solve for this unknown, and there's a very specific unknown that goes with it to make it true. Same thing over here. So when we look at this, we're going to say, let's just y equals sine of x. Alright, you have an input and an output. So it's just an equation, just like over here, we were able to identify it as just an equation. So if you did swap these around, when we wanted to solve for y, we had this ability to undo this multiplication of 4 to get our y by itself. Well, we need a way of undoing this sign, so that's when we have this inverse sign that comes into play that will cancel off that sign. But whatever you do to one side, you have to do the other, just like over here. So this is now indicating to me that I am doing this inverse operation to a sine function. So here's my new equation. Alright, if we were to look at the tables for this, we have y equals sine of x. If you were to look over here and say, Alright, let's input, for example, pi over 6. If you look at your unit circle, you would look at the opposite over adjacent of this angle pi over 6 and you would get 1/2. If you were to plug in pi over 4, then you would look at that specific angle in that triangle and you would say, alright, the side to side ratio of the opposite over hypotenuse is the square root of 2 over 2. So at this point, what I want to say is now we have this inverse operation that looks like this. And we need to have a way of looking at it as, alright, if you looked at the side to side ratio, where you had a triangle where the opposite over the hypotenuse was equal to 1/2, then you know that it would be linked to the angle pi over 6. Okay, if you looked at a triangle and you noted that the opposite over the hypotenuse was the square root of 2, then you would know that it was linked with pi over 4. Okay, so the whole idea is now we're in this place where we do not know the angle, but we do know that side-to-side ratio, so now we're just trying to solve for what is this unknown angle, right? Just like we were over here. A function must be a one-to-one function to have an inverse function. What that one-to-one means is it has to pass not only the vertical line test, but also the horizontal line test. And the reason is because if you were to say, alright, here's my original function, sine of x, and I plugged in these certain hotspots, the 0, the pi, the 2 pi, note that they're all linked with 0. So when you turn this around and you ask yourself, alright, let's go ahead and flip these. So these are all flipped. Now the question is, again, for a function to be a function, for every input, there should only be one answer output. And if I said if you plug in 0 for this x, well, there are several angles that would match up with that side of that opposite over hypotenuse of being 0. So there's that not passing of the horizontal line test. So what we actually do is we restrict it. Someone at one point in time restricted it to negative pi over 2 to pi over 2. So we're only going to be looking at this section. So do note that that's only going to be from negative pi over 2, that's right here, to pi over 2. We're only looking at quadrants 1 and quadrants 4. Because in just the unit circle alone, if I ask you what angles have the sign of 0, well, you would be looking at this one right here and this one right here. There's two different answers. So which one is it? Well, it's going to be this one because it's going to fall within that restricted output, that restricted range. So right here, that's where we're going to be looking. So the domain and range, if we did restrict this, the domain to this sign of x, the domain was from, remember, all possible input values were from the negative pi over 2 to through pi over 2. Okay, that was our interval notation right there. Sorry, I'm going to use the square brackets to include it. So there was my domain, and then my range, the y values that it ranged from was from negative 1 to 1. So from negative 1 to 1, those were my possible outputs. Alright, so now remember, everything about this inverse sign is going to swap. So if we looked at, this is just a notation for inverse sine, arc sine of x, the domain now is going to be what the range was, and the range is going to be what the domain was. Okay, so this we're just going to be looking at outputs that are in quadrant 1 and quadrant 4. Okay, it's right here on the unit circle. Alright, so the inverse sine, the two notations as I've kind of been bringing up, it's either they use the arc sine of x or the sine to the negative 1 of x, and both of these just mean inverse sine. And what we're then doing is we're saying, alright, we're trying to find out what is the angle whose sine is x. So we're going to do a practice with this. Let's try to evaluate what is the arc sine of 1/2. So again, what we're looking for is an angle. We're trying to find an angle such that when you took the sine of it, you would have gotten 1/2 as the opposite over hypotenuse. So looking at that unit circle, what we could say is I could draw this triangle right here and see that one works. Okay, and I would say if I took the sine of this pi over 6 here, I would have gotten 1/2 over 1 for that. So this answer right here is going to be pi over 6. Right, and again, that comes from pi over 6 is the angle whose sine is 1/2. We're trying to find the angle whose sine was whatever that input was. So here we have it. One thing is you could probably look over here and say, oh, but this triangle also had the sine of 1/2 or the y value of 1/2. But again, what we're only doing is we're restricted to looking at quadrants 1 and 4 for the sine. Alright, here's another one. This is the other notation. So to evaluate this trig function, what we're trying to do is find the angle such that when we took the sine of that angle, we got the square root of 3 over 2. So when you look at this right here, I'm looking at it and thinking that's that triangle that's going to get me for the opposite side the square root of 3 over 2. It was that y value. So here I'm going to look at pi over 3. And again, if you wanted to, you could say let's take the sine of this side to undo that, the sine of this side, and what happens is you get that expression, well, the sine of pi over 3 is equal to the square root of 3 over 2. So we found, when we got the pi over 3, we found the angle whose sine was the square root of 3 over 2. Alright, so I'm not going to spend as much time, but I am going with the cosine and tangent, but we again need to restrict which outputs we look at. So the domain for the arc cosine is going to be from -1 to 1. The most important part is when you're looking for your answers to these arc cosine functions, you're looking in quadrants 1 and quadrants 2 because we restricted the domain to just this piece right here. Okay. So we're going to look at the notations of cosine. Again, it's using either that arc or that -1 exponent. Again, what we're doing is we're looking for the angle whose cosine is a certain side-to-side ratio. So we're again going to pull up the unit circle. If you were to write this, arc cosine of 1/2 is equal to some sort of angle, you could go ahead and say, well, to get rid of this arc cosine, we can just take the cosine of it, right? These are inverse operations, they cancel each other out. So then we would have to do this to the other side. So really what we're asking ourselves is, the cosine of what angle is equal to 1/2? We are restricted to quadrants 1 and 2. So cosine is kind of the weird one out. It's going to be looking at the top half of the circle. So let's now ask ourselves, what angle that when you took the cosine of it would equal 1/2? So we are looking for the adjacent legs, which happen to be those x values. This one right here is going to be the one that we're looking for. Because if we were to take the cosine, so I'm going to say that this is equal to pi over 3, because if we were to take cosine of pi over 3, then yes, we would have gotten this 1/2. Here's another one. So again, we're using our different notations. So I'm going to go ahead and say this is equal to, I'm going to be looking at the top half, and what I'm going to notice is this is the one that I'm looking for. Because if I were to take and look at the angle, and this right here is our 5 pi over 6, what we're saying is that the cosine of 5 pi over 6 was equal to negative square root of 3 over 2. So tangent, we're going to restrict it to this part right here. It's the same as sine. We're going to look at from negative pi over 2 to pi over 2. So this, oops, I never labeled this, but this is again quadrant 1 and quadrant 4. It's this side of the unit circle. Here's negative pi over 2, here's pi over 2. Alright, so tangent, same thing, we have those notations. I'm going to try to evaluate this. Tangent is a little bit more tricky because you can't just simply look at the x and the y values. So if we were to look at this arc tangent of the square root of 3 over 3, keep in mind we're trying to find an angle. So arc tan of the square root of 3 over 3, and we're trying to find an angle, you could always again say, let's look at it this way. Let's get rid of that arctan, tangent Oh, that's an angle. So tangent of what angle is equal to the square root of 3 over 3? Unfortunately for tangent, you can't see as clearly what they are. You're going to have to start to get used to what are the tangents, where do you see the square root of 3 over 3. But if you are in any doubt, you're going to actually have to maybe do some guess and checks for now. So I'm only looking at quadrants 1 and quadrants 4 due to the restrictions that we made. So for the arctangent, we only can get answers, or the range, the possible output values, in quadrant 1 and quadrant 4. So let's maybe guess some. I'm going to go so far as to say that we're only going to look in quadrant 1, because we're going to be taking the opposites divided by the adjacents, and we want them both to be positive in order to have this positive side-to-side ratio. So what angle is going to produce the square root of 3 over 3 when you take the opposite divided by the adjacent? So here I'm going to maybe guess and check for the time being. Tangent of pi over 6, what would that have gotten us? Well, we have 1/2 as the opposite over the square root of 3 over 2. When you change that to multiplication, we're going to get this problem right here. Okay, these reduce to be just 1 over 1. And so what we get is 1 over the square root of 3. When we rationalize this, we get exactly what we want, because we have now gotten the square root of 3 over 3. So I got a little lucky here, but what this is equal is 2 pi over 6, because pi over 6 is the angle whose tangent was the square root of 3 over 3, whose side-to-side ratio was that. Okay, let's go ahead and look at this one. So sorry, let's say -1. Okay, so hopefully you could kind of see that it's either going to be these ones, these hot spots. The tangents are kind of the weird rationalized answers. If I were to look at this one, tangent to the -1 of -1, again what we're trying to say is we're trying to find the angle that when you take the tangent of that angle, you get -1. So these 45, 45, 90 triangles are what we're going to be keying in on. And I do want it negative, so it's going to be this angle right here, which would be our negative pi over 4. Okay, so tangent of negative pi over 4 is equal to -1, because I changed it. When we do arc sine, we're going to be looking at quadrants 1 and quadrants 4. When we're doing arc tangent and evaluating side-to-side ratios there, we're going to be looking for outputs also on that right side of the quadrant. Arc cosine is the weird dog out here. You're going to be looking at quadrants 1 and 2, so the top portions. So I'm going to go ahead and start doing some of these problems. If I look at number 1, what they have is arc sine of 1/2, and they want us to evaluate. So again, I am looking for the angle whose sine is 1/2. So when we look at this, so sorry, the angle, I did an example like this earlier. We're looking here, that's going to be, well, the pi over 6. Okay, it's not this triangle. It could have been, but we only want one possible answer. That's why we restricted it to this side of our unit circle. Number 2 was the arc sine of 0. So we're looking for an angle such that the sine, or the opposite leg, was 0. That's what that would be saying. So this one right here would be 0 radians. Okay, because that would be the angle that would have gotten us to have no up and down movement. Number 11, half. So now I'm going to be looking at particularly these two quadrants, so this highlighted circle, and what we're going to say is we're trying to find the angle that the cosine was -1/2. So if you look at these, you can draw a triangle here and say, oh, does that work? Does that pi over 3 work? Well, does the cosine of pi over 3 equal -1/2? In this case, no, we needed the negative, so we're actually going to go with this triangle right here. So this 2 pi over 3 is what we're going to want because the cosine of 2 pi over 3 was equal to negative 1/2. We want to be able to write it back and forth like that. And then finally I'm going to do number 14 with you. If we had tangent to the negative 1 and then the negative square root of 3 over 3, again, the more you do of these, the better that we'll get. So here is the arc tangent that we're looking at. We're restricted to only this portion of output values. We can't output any angle over here. It's between that negative pi over 2 to pi over 2. So our answer that we're going to be looking for is some sort of angle that when we took the tangent of it, we got the negative square root of 3 over 3. This is going to possibly do some guessing and checking, but what we had done was that pi over 6 and got the positive square root of 3 over 3. So let's check this angle right here, negative pi over 6. And if you went ahead and did that, tangent of negative pi over 6 is the same thing as the value in 11 pi over 6. Okay? But what you're going to get is you're going to ask yourself what is the opposite over the adjacent of this particular triangle, and you would say, well, opposite was negative 1/2. The adjacent was the square root of 3 over 2, and so when you simplify this, yes, you are going to get what you were aiming for because we rationalize it, and yeah, we did get this. So this is our answer to number 14. Alright, you still have some more practice problems with this. You're truly using the unit circle as you look backwards with these relationships of side-to-side ratios and angles.